This is Jianhao, and I'm rehearsing for a presentation that I might be doing tomorrow. Okay, so hi guys. Today I'll be talking about going from your math concepts like P and C to the ideal gas law, and this is under the realm of statistical mechanics. So yeah, I'll be briefly going through how one can think about particles in terms of combinatorics, n choose 2, n choose 3, and then eventually lead to the laws of thermodynamics which we learn in physics. So this is the topic of my lecture today, and I hope that it'll give you a sense of perspective of how how relevant the math we are learning is to the real world and how everything links together. So here's the agenda. I'll first talk about temperature from a combinatorics point of view. What exactly is temperature? Then I'll talk about something called the Boltzmann Distribution, and I'll talk about gases, and finally end with the ideal gas law. So okay, I happen to bring two Milo today, so if you guys, if I ask questions, please participate. Yeah, if not, I look very dead on the video. If not, my talk looks very boring, and yeah, so I would, to make it fun, because competition drives innovation, right? I would give the Milo to the person who answers the most questions, or for each answer, uh, I I'll give you a certain points, So if the better your answer is, the more points you get. So in the end, I'll give Milo to the people with the most points. So yeah, please answer my questions. So first, let's start off with some simple vision of permutations and combinations. If I have 100 coins, right, and each coin has a head and a tail, how many ways are there to have 50 heads and 50 tails? Anyone? Okay, yeah, so correct. It's just 100 choose 50, right? And that's a big number. Then what if I have 53 heads and 47 tails? Then it'd be 100 choose 53, which is slightly smaller than 50. And if I have 90, then it's even a smaller number. You see, it's a few magnitudes off. So let's talk about the concept of macrostates and microstates. So how is it relevant to P and C? We'll see later. So if I have a system of n particles, what are the different ways you can describe n particles? So there are two different perspectives. One is the micro and one is the macro. So similar to micro and macroeconomics, right? The micro is focusing on each individual firm, each individual particle. So the micro asks what is the current state of each individual particle. I'll give an example later. And for macro is talking about something called macro variables, macro um, thermodynamic variables that describe the entire system as a whole. Such include pressure, volume, number of particles, temperature, and stuff. So if I have an example, if there are n particles, each particle is described by a position and a velocity, right? So in the end, there's 6 numbers that describe each particle. So if you have n particles, you need 6n numbers to describe the entire system, to know the state of every single particle in the system. So that is what you call a microstate. If you know a certain microstate of the system, a microstate of the system is the knowledge of the position and velocity of every single particle. But of course, this is very difficult to do, because how are you going to track each particle? How are you going to see where it moves, right? So uh, another description is the macro state of the n particles, which is let's say a single number describing the entire system, which is like the total energy, or like the temperature. So this the difference between microstate and macrostate. I'll give more examples later on. So yeah, so let's say we have two particles. An example of a microstate is these 12 numbers over here. These 12 numbers here specify a specific microstate of the particle. Of course, there can be many different 12 numbers, sets of 12 numbers that describe the different microstates, but this is just one of them. And a macrostate, for example, will be saying the total energy is 24. So you can see that macrostate is much simpler description of the microstate. But right now this seems very useless, right? So what if I know the position and velocity of every single particle? How am I going to track the changes throughout the entire system? Well, that is where statistical mechanics in physics steps in. It is the link between the microstate and the macrostate, and you'll see the logical flow later. So another illustration is that this is one example of a microstate that has a macrostate of 24. Well, is there other microstates that can lead to a macrostate of 24? The same macrostate? Yes, there are in fact many microstates that lead to the same macrostate, and one example is this other microstate where I can see I swapped the number 2 and 4. Yeah, so point is there are many microstates that correspond to the same macrostate. It's entirely possible, and later we'll be able to count this with combinatorics. So, as mentioned, there are many microstates that correspond to the same macrostate. Now let's have a simpler example. If I have a bunch of particles, let's say 100 particles, and each particle can have two energy levels, 0 or 1. So if I know the energy level of every single particle, I know the microstate of all the 100 particles of the entire system. But if I say that there's, let's say I want to ask the question, how many microstates correspond to the macrostate of a total energy of 25? So the answer would be 100 choose 50. 100 choose, yeah, how many? 100 choose 50, which is exactly exactly the coin example we had just now, right? So what if I ask, yeah, so you can see that we can, if our energy levels were simple like 0 and 1, then we can easily ask the question of how many, we can easily count the number of microstates associated with macrostates. Now, of course, for systems with more different energy levels, like energies that depend on that, for example, you have infinite number of energy levels, then the counting will become a bit harder. But at the core, the idea of microstates and macrostates still technically apply to those situations. So let's define something. Let's define the counting. This counting function which counts, given a certain macrostate with energy E, what are the number of microstates corresponding to that macrostate. So for example, in the previous example of 100 particles, each having energy 0 or 1, the way to count the microstates is with the function 100 choose E, right? So C is a function that helps you count the number of microstates corresponding to a macrostate. So this is a very simple idea that we can use combinatorics to help you tackle. So logically speaking, if one law in statistical mechanics is that every single microstate is equally probable, meaning that if you have a whole bunch of, so this is where the microstate and macrostates, the ideas sort of converge, because previously we said that how is it supposed to count all the microstates, right? So instead of saying that we need to count each individual microstate and track the evolution, we said on average, right, the probability of each macrostate happening corresponds to the number of microstates there are. So just imagine that every single microstate is equally probable. Okay, every single possible state of each individual particle is equally probable. Then certain the macrostates which have more microstates corresponding to it will be more likely, right? So the probability of a macrostate, it is proportional to the number of microstates associated with that macrostate. Clear? Is that clear? Okay, don't worry, let's give an example. Let's say I have a coin example again, and this time I have 3 coins. Okay, so we have over here we have 8 boxes, and each box represents a particular microstate. Then the energy levels above represent the different macrostates. So in this case, you can see that for the E equals to 2 column, you see that there's two particles with energy 1, and where 1 plus 1 is 2. So yeah, so over here we have the macrostates described by a single number, and over here we have 8 different types of 8 microstates, and each microstate is basically the knowledge of every single particle, the state of every single particle. So let's say I want to ask, so you can see that for the macro state E equals to 1, there are 3 corresponding microstates. And so we say that for the counting function of the E equals to 1 macro state is 3. Okay, so I hope that the concept of macro and microstates are very clear now. Let's talk about two systems. So right now so far we have just dealt with a single isolated system, and we know the probability of finding the system in a particular macrostate. So what happens if we put two systems together in thermal contact? What does that mean? It means that they can transfer energy to one another, right? And you might have heard that energy flows from a body of higher temperature to a body of lower temperature. But what exactly is temperature in this case? So we'll see with the definition, with the tools that we've developed so far, we can define a simple notion of temperature. So let's say I have two systems E1 and with two systems represented by these two boxes. Let's say right now they are isolated from one another, E1 and E2. The first one has energy E1 and the second one has energy E2. So you can imagine that they are, so first one has energy E1, second one has energy E2. Then the total energy is just the sum of two energies. Then let's say I allow them to flow energy between them, not particles but just energy. So we know that the total energy E is still conserved. So but eventually, since energy flows between them, how much energy will eventually be allocated to each box? First guess is maybe in the end that both energies of the boxes are the same, but that is wrong because thermal energy does not correspond to temperature. We'll see why this is wrong later when we present a more correct answer. So the correct way is to maximize. Remember what we said previously about probability of a certain microstate being proportional to the number of microstates associated with it. So the combined microstate is just the product of the first system and the second system. And basically we want to maximize this function over here. So you see on the right hand side we have so if C1 describes C1E1 describes the number of ways it describes the number of possible microstates associated with the E1 macrostate, and C2E2 describes the number of possible microstates associated with the macrostate E2, then C1E1 times C2E2 is just equals to the total number of microstates in the system, right? And we want to maximize, and this total number of microstates is dependent on one quantity. It's dependent on the energy in E1, because once you know the energy in E1, you know the energy in E2 by conservation of energy. So the upshot of this is that there's this function of E1 that you want to maximize, and that maximizing this function, and upon maximizing this function, you would be able to you'll be able to know how much energy is allocated to each of the systems. So what happens when you maximize something? You differentiate. So the parameter here will differentiate with respect to is E1, and you see that all this math here is actually just everything you have learned before, right? It's actually just product rule and chain rule. So if you follow along, the steps is you can check for yourself. It's just product rule and chain rule, and then you rearrange it, and in the end, what do you get? You get that the derivative of ln C1 with respect to E1 equals to the derivative of ln C2 with respect to E2, and this condition this is a condition that helps you maximize the microstate. Now if we define 1 over temperature equals to this function, then we can see that the macrostate that is the most probable after the energy transfer is the one where the temperatures are equal. So this is just stating the zeroth law of thermodynamics. It's basically saying there's a temperature function associated with each system, such to help you allocate, to help you determine the amount of energy left in each system after. It's basically telling you there's this temperature function that helps you that it's basically telling you that in order to determine how much energy each system gets in the end, you need to set the temperatures to be equal, and that's where temperature is defined. So this is the definition of temperature. This is statistical definition of temperature. So it has been a bit it might have been a bit confusing up to this point, but just know that remember that we started off from the counting of microstates within a macrostate, right? Using combinatorics, and from this combinatorics point of view, we determine that the probability of a macrostate is corresponding to the number of microstates that belong to that macrostate. And then after that we consider what happens when two systems come together. We consider the combined microstate, and by maximizing the combined microstate, we statistically determined what is the condition for the number of microstates to be maximized, and that condition is precisely saying that the temperatures of the two bodies are equal, where temperature is defined here. So this is a temperature from a very ground up point of view. And yeah, so now let's go on to something called Boltzmann distribution. So I won't have too much. So over here I'll have the baby hand wavy, but essentially we're asking the question of if we have a single system. So previously we have only been able to count the microstates given the number of microstates corresponding to a macrostate, right? But now let's say we have a single system and we know its temperature. Then it can be derived that the probability distribution of microstates is given by this formula over here. This is called the Boltzmann distribution. So using this probability, you see there's a proportion here. While imposing the condition that the sum of all probabilities must be equal to 1, which we have learned before, we get something called the partition function. So Z is essentially just a normalization factor, right? It's the sum of all the probabilities, and then that ensures that sum of all the probabilities equals to 1. So this is, in the end, the bottom formula here is the probability of a microstate happening, a probability of a system being in a particular microstate, and that probability is given by exponential of negative energy over temperature, where the energy En is the energy of a particular microstate. So they've talked about Boltzmann distribution really quickly. So let's go to something really cool. So how do we calculate average energy? So right now, right, we have a box of particles, and we can only say that, oh, this particular microstate occurs with probability 0.1, and then this other microstate occurs with probability 0.2. But how do we calculate? So you can see that given a particular temperature, the energy is actually not fixed, right? Because if you are in you don't know, because the energy is actually given a particular temperature, the energy actually can fluctuate, because you know that the energy we don't know so right now, right, given a particular temperature of the system, we do not know the exact energy. And this is because if your system is in one microstate, we only know with a certain probability that this system is in a microstate 1. We only know the probability. We can't be certain that probability that the system is in that microstate. We only know it with a certain probability, same as the other microstates. So let's say it's like saying that, oh, I know is this way, I know is this microstate 10% of the time, and this one I know is this microstate another 10% of the time, but I don't know what the but because the energies of the two different microstates are different, I can't say with certainty that, oh, this system has energy of has this energy or this energy. I can only say that I know the average energy. And remember that we learn in probability that the average value of something is just the expectation value. It's just the expectation value. So you take so you sum over all the microstates. You take the energy of each microstate times the probability of the microstate. So does this line make complete sense? I hope it does. But here's where it gets really interesting, because from this definition of using probability theory, right, we only got this from probability, but with this probability and with the definition of Pn, we can express everything in terms of the partition function. So what does this mean? You see that Pn that follow the manipulation, it goes to the next line, right? And then in order to bring En down, we do something tricky. We take the derivative with respect to beta. And if we take the derivative, then we can pull out the derivative from the sum. And actually this is just the derivative of the logarithm of the partition function. So this is something pretty incredible, right? So in the end, what do we get? We get the formula that the average energy is just the derivative of the partition function with respect to this inverse temperature. So this is the power of the partition function. And there's a lot of other quantities that can be calculated from the partition function, like pressure is one of them. So I hope that's clear. So if the upshot of this is that once we know the partition function of any system, remember the partition function can be calculated from knowledge of the energies of the microstates. Once we know the partition function, we can calculate all the properties of the system. So let's go to an example. So let's see, we are now ready to tackle the monoatomic gas. So how do you calculate a partition function for a single gas particle? Well, you know, first, in order to calculate the partition function, you need to calculate the probabilities. Now, what is the probability? Is equal, as long as you know the energy of a microstate, you know the probability of a microstate. So what is the probability of a microstate? What is a microstate again? It's the position and velocities of each particle, of the particle. And it can be, so, and since we know the energy in terms of position and velocity, which is just half mv squared, then we can calculate the probability of a particular microstate. And if you do the summation of all the probabilities over all the microstates, which is actually an integral, something called a Gaussian integral, then you get this. So this, what do we need to take note over here? We only need to take note of two things. Although it looks like a very scary formula, but there's only two things. Number one is the volume, and number two is the temperature. So the partition function only depends on the volume and the temperature. The rest are just constants. So we can extend this to n particles, which turns out to be just this formula, just z. It's just one of them to the power of n divided by n factorial. which is something to do with the indistinguishability in quantum mechanics, but yeah. So with this formula we can already calculate the average energy. So we remember the formula that energy is minus the derivative of ln the partition function. So we just calculate it. Remember, and we only need to take the derivative with respect to temperature. So in the end, we just get 3/2 nkt, and that is in fact the formula that we see in statistical mechanics, in thermodynamics. So it's very cool that you can go from concepts like P and C, right? We went from P and C, then we defined so from P and C we managed to define something called temperature, and from temperature we managed to define the Boltzmann distribution, where the Boltzmann distribution tells you how probable it is for each microstate given a certain temperature. From the Boltzmann distribution, we managed to obtain formulas for average energy in terms of the partition function, and from the average formula for this, we managed to derive the average energy of an ideal gas. So now, what about diatomic? Does anyone want to hazard a guess of what diatomic is? And yeah, in order to encourage participation, I'll be giving one of the Milo to anyone who tries to answer. So anyone? So for the previous one we got 3/2, right? How do you get 5/2 for diatomic? How does diatomic differ from monoatomic? Well, the answer is rotational energy. So remember from the very beginning we said that the partition function depends. So if we trace back, right, the dependence, we realize that the average energy calculation depends on the partition function. The partition function depends on the probability distribution, and the probability distribution depends on the energies of each microstate. So what has changed? It is the energy of each microstate. When you have diatomic molecules, you have more degrees of freedom. You have rotational degrees of freedom, and these rotational degrees of freedom, they contribute to the energy of a microstate, because you have half I omega squared, right? So this rotational energy would trickle down to the probability distribution of the microstates, to the partition function, which would then affect the average energy. So the calculation on the right over here, so the calculation on the left is just the energy of, you don't need to know it, but I'm just showing it here. You don't need to know the details, but it's just the energy of rotation. And then the right here is the partition function for rotation. And when calculating energy, this additional rotational partition function will give rise to extra factor of kBt. And 1 plus 3/2 is 5/2. So that's how you get 5/2 for the diatomic gas. So now we have covered all this already, and let's go to the last part. So PV equals to nkt. There's two methods. One is going through the kinetic theory of gases, which makes is much more convincing. There's two methods over here. The left one is a longer one, but I'll be showing the right one because it's just a formula. So the point is, there's also something called the free energy you can define, which is this quantity over here, and then using that you differentiate the free energy with respect to volume, you can get the pressure. So over here on the right is the calculation. Most of it is just constants. The only thing you need to take note over here is volume. So besides volume, right, the rest are actually just constants. So often in physics you see scary formulas like that. you see scary formulas like that, but most of them are actually just constants. So anyway, you take the derivative and you get P equals to kBt n over V, which is just PV equals to nKt. So that is the exact formula. Yeah, so I hope that now we've covered all the 5 agenda points, and the key takeaway I want you to have from here is that we can think about particles from very basic first principles using just ideas of permutations and combinations, and eventually we work our way up, we have developed more tools, and we can eventually obtain results like PV equals to nKt, which seems very detached from thinking about particles from first principles, but you see that statistical mechanics is a very coherent logical flow, and this also reflects something about how we think about life. So the beautiful rests on the foundations of the necessary. If you are ever trapped in a certain problem, it always helps fundamentally to think about what caused the problems, like what underlies your problems, and then tackle the problems at their roots. And from this first principle thinking, you can build high high up, like how we got from thinking about particles from permutations combination, we went foundational to something complicated like the PV equals to nKt formula. So anyway, that's the end of my presentation. Yeah, thank you.